Hello, I'm Michelle Davis of the Center for Manufacturing Research at Tennessee Tech University in Cookeville, Tennessee. Thank you for joining us today. And welcome to the Spring 2020 Golden Eagle Additively Innovative Virtual Lecture Series. This is the 9th semester we have produced this popular and informative series. The series is hosted by TTU's Center for Manufacturing Research and the iMaker space at TTU. Additive manufacturing is a focus of both entities, and as such, this short virtual lecture series has been planned to highlight the best practices, potential problems, technological advancements, innovations, and scientific contributions in additive manufacturing with expert talks from various institutions, industries, R&D centers, and laboratories. Today, we are honored to hear from Dr. David Bu Pedersen, Senior Researcher, Department of Mechanical Engineering, Technical University of Denmark. His talk is titled A Holistic Approach to Achieving the Best Possible Component for AM Architectures for Vat Photopolymer and Laser Powder Bed Fusion Systems. The speaker will provide his contact information for questions after the presentation is over. Thank you, and I turn the presentation over to Dr. Pedersen.
Hello, everybody. And Michelle, what a wonderful cat you've got. Looks like totally like mine. It's completely black.
Yes.
Yes, so is mine. So is mine.
He wanted to be on camera.
Yeah. Hello, everybody. It's such a pleasure to be able to meet here online with everybody. This has become the norm in Denmark, where I reside. We have been completely shut down by the COVID-19 virus for now 3 weeks. And currently my kitchen is my office. So that hopefully means that I've got all my skills honed with respect to mashing buttons in Zoom meetings. So let's hope that everything here pans out as we expect to. I would like to start by sharing my screen. See if we can get that up running here and here. And here. Wonderful. So my speech today is entitled A Holistic Approach to Additive Manufacturing. And what I hope to do with this presentation is to inspire you to see the world of additive manufacturing ever so slightly different than what you might be entitled to do. And I will do that by first reflecting over the state of the industry, how it is, and then show you some of the results that we've been working with in our labs here in Denmark. But before we go ahead, as I said, the kitchen is my office right now. I'm very much an experimentalist by nature. I do whatever I can to not sit in front of my computer, and therefore, it's very unusual for me to sit for 7-8 hours straight on my behind and just mashing buttons. So as you can see, I've set up my entire kitchen table as a little workspace. All my experimental facilities are at the university, and I did not manage to get any equipment out of the university before leaving. So what I chose to do instead was to one of my hobbies outside of academic life is to building race drones and flying race drones. So right now, when I'm just too fed up with mashing buttons on my computer, sitting in online meetings, I shut down the laptop for a few minutes just to solder up a few wires on the new race drone I'm building. So that's also just for you to have a feeling of who I am as a person outside of the university. I'm just a nerd. So going back to the topic, additive manufacturing, if you ask me, is very much the Wild West. Everything goes. And it has been more clear than ever over the last handful of years, given the fact that the monopoly that was in the additive manufacturing industry has really opened up. And we see a lot of new initiatives and a lot of new players. And we see additive manufacturing being presented as the next big industrial revolution. And that is peculiar to me, because when I was 8 years old, back in 1988, same story was in the news. And you can ask yourself, how long time does an revolution actually take? Is it multiple decades, or is it in an instance? Well, if it is a revolution, it happens quickly and not over some 35 plus years. So I would much rather call it a slow and incremental evolution, like every other technology that hits us. I mean, the internet is around the same age, and just look at how that has evolved, and frankly, how little additive manufacturing has in comparison to. But nonetheless, everybody seems to buy a ticket first class on the hype train, going with this idea about additive manufacturing being the next industrial revolution. And you see all these, what they call research initiatives, such as additive manufacturing of food. In this case, it's a pizza. It's a flat, two-dimensional almost object. Does not make sense to me. We see the attempt of 3D printing textiles. We see all sorts of attempts to using additive manufacturing for something just because we can, and maybe not because it's necessarily a good idea. And here it's really important for us to relate to the fact that additive manufacturing is a two-faced phenomena. One thing is what is going out between all these fortune tellers that try to predict the future, amongst all the big consultancy groups, such as even a consultancy group as McKinsey runs with the idea of it being a revolution, and then what actually happens in niches in the industry. And that is also why I am very careful about calling what I do additive manufacturing and not 3D printing, in order to differentiate myself from the hype and making my impact in where there's actually some true relevance to the technology. But you probably all know that this is a good example of when additive manufacturing makes sense. It's not a pizza. Oftentimes, when we look at these industrially applied additive manufacturing systems, they look a bit like this. It is very much a black box, both in appearance, but also in how you operate it. In many cases, you can be the biggest expert on planet Earth, but you're automatically rendered a user because the machines are very proprietary. They're very much closed down. And that's also the dirty little secret about additive manufacturing. We might be working with what, in comparison to what is the industrial state of the art is, then it is a precision instrument. And then the dirty secret is that afterwards, there's so much manual labor involved. There's stuff like this. So what about our tolerances? Do they hold up? Can we trust what we've been doing? What is it actually that is being produced by the machine, and which errors are introduced afterwards in post? And many of these questions are hard to relate to if you are tied up with an industrial supplier network, working on an industrial machine. You are more or less only allowed to do what the manufacturer wants you to do, and not really experiment. And that's a shame, being an engineer, being an experimentalist, wanting to push boundaries, that you then end up realizing that your big, very expensive additive manufacturing machine tool is a proprietary closed system. And I really cannot stress that clearly enough. I think the industry is unreasonably closed. I feel with many of our industrial systems that we have historically had in our lab, many of those has been retired from the fact that they are so proprietary. I feel that I've bought myself into an inkjet printer model. If you buy an inkjet printer, you are married with an ecosystem of ink and novelty paper to put into the printer that needs to come from the original equipment manufacturer. And if you break those rules, then they don't want to, in any way, shape or form, service you as a customer. And it's the sad state of additive manufacturing as well. We see it on photopolymer printers. We see it on the extrusion-based filament printers, that even consumable materials are being locked down with RFID tags. We see a lot of nonsense revolving around how materials are being being sold and presented to industrial customers. In this case, I'm censored out the manufacturer because it doesn't really matter. But in this case, we are dealing with a simulated polypropylene. Oops, a simulated polypropylene. It can 3D print precise prototypes, and it looks and behaves like polypropylene. Well, let's think about this. This comes from a Vat photopolymerization system. Then it's evident for us that this is a thermoset, not a thermoplastic. Polypropylene is a thermoplastic. There's a world of difference between a thermoset and a thermoplastic. Already there, the story crumbles and breaks down. If we then begin to do material testing of this material, it will not be polypropylene at all. It will have a different wettability when in contact with moisture. It will have a different thermal degradation. It will not be able to be reused and remelted. So if the user here thinks that, oh, I can set this off with my other plastic scrap for recycling, no, you cannot. You can only burn this to get rid of it. It is super hard for a design engineer wanting to make use of additive manufacturing to pick and choose the right materials when you are faced with something like this. In many cases, the sad truth about the industrial state of additive manufacturing is that you also buy yourself into a subscription model when you buy the machine. For example, many of the powder bed metal machines come with melt pool monitoring systems. You've paid dear money for having that hardware in your machine, but oftentimes you are forced to only extract data through a black box. And for that black box, you need to sign up for a running subscription model to access your own hardware. And there's no other way. It's encrypted, locked down. You also see it on materials for powder bed metal. You might be faced with a manufacturer that claims that their machine is fully open, and you get tempted and you buy it, only to realize that yes, it is fully open, but whenever you want to introduce a new powder in your machine, you are forced to dish up with money to get the company to provide you with a new build style for the machine for that specific powder. If you do not do that, they will not service you as a customer. Imagine if this was the world of CNC machining or injection molding, or if you were having a big forging press or a sand mold forming press for the casting of cast iron, and you were faced with such a business model, you would say, thank you, but no thank you. I'm not buying your system. But for inexplicable reasons, it's okay because it's additive. And that really makes it hard for us to understand what is actually going on there. How do I quality ensure? How do I get the best part out of the machine? Let's just face it, the manufacturers of these additive manufacturing systems have not optimized their machine for production speed or for the fidelity of small features of the components you are manufacturing. They have optimized the machines for robustness such that if the operator is a monkey, the machine will still run. There's only one start button to press, and there's no decisions that you really need to make as the operator. I know that I'm overstressing the situation a bit here, being a bit granular. Might not be that bad, but still when we compare it to conventional manufacturing, it's a world of difference. And we just have to suck it up and live with it as researchers and engineers. So if you ask me, additive manufacturing is truly the Wild West, and everything goes. And the monopoly that was formed by patents back in the 1980s, though the patents are no longer standing, there is still the attempt to close down the industry by the big players there to keep status quo such that it will still be a lucrative niche business to manufacture using additive. So with that introduction, then let's have a look at the word holistic or holism. It is a theory where we take a systemic approach to what we are doing. We step back and ask ourselves, what is actually going on here? And if we relate that to the pitch I've been giving you as an appetizer to this presentation, then a holistic approach is to not accept that these machines are black boxes and you cannot see inside and you cannot understand the different subsystems, because then you cannot use the machines to their best. That is why we see a lot of research on CT scanning, because researchers, many places, have an additive manufacturing system that they cannot touch and tweak and optimize on. So they are only left with activities such as design for additive, qualification of the components that comes out of the machine, and the machine has just run with a standard parameter set and a standard material, and then they pick up research where they can. That's not a systemic approach. And to be frank, it's getting a bit boring to attend yet another conference, hearing yet another presentation of CT scanning of a gas turbine blade. I cannot count how many of those I've heard. A systemic approach could be to begin to question what is actually going on inside the machine. We have some design for additive that we need to obey with, because there are some limitations with these processes as with everything else. One of that can be the fact that we are still using a format from dating back to the dinosaurs in terms of specifying geometry for additive manufacturing, the STL file format. Then we have the actual process itself, and we have what is going on as post-processing. And unless we really begin to try to understand each and every single step throughout this process chain of just making one component using additive, it is really hard for us to optimize anything. And ideally, we should be able to pull in all available levers throughout each and every step in this process chain, especially the one called additive manufacturing. So, taking a holistic approach to achieving the best component quality, how can that be done? Well, be a systems thinker. Think of what is inside this system that I'm standing in front of. If it's a metal powder bed fusion system, I have a high-powered laser. It's quite easy to understand how they work. It's a fiber laser. It's probably diode pumped. It's single mode, most likely. They're being used in abundance. I can educate myself in how such a laser system works and understand it intimately. Then there's a galvanometer head and an F theta lens that scans and focuses and shapes the laser light. That is quite simple theory that you need to understand within optical systems to figure out what kind of errors do I introduce through that system if it is not calibrated correctly. If I see pincushion or barrel effects in the scan field of my laser system, then how can I link that to the optical theory and understand how my machine is out of calibration? Also on a commercial system, even though you might not be able to change that calibration without getting a technician to come and visit you. Then what about the welding process? Well, in a little centicube by 1 by 1 by 1 centimeter, there's roughly 200 meters of laser welding. And laser welding is very well known as an optophysical process, and you can understand that very intimately. And already when you begin to break down the system in front of you and question how does it work and how can I understand the relation between errors I see on the workpiece and their causes within the system, you will already then be a much better engineer in optimizing your additive manufacturing process for any given component that you are making. If we consider what is going on all the way from preparation to post-processing of a component that we are manufacturing, it is indeed a cyber-physical system we are dealing with. We have the physical process, we have the digital aspect of the process. The digital aspect from job preparation is how do we generate the cat body? How do I tessellate that to an STL file? Is it a closed hull as it's supposed to be? What about the preparation of the machine? How long time do I need to warm up the machine before it reaches steady state? All of these common practices in precision manufacturing engineering can be applied here. And it's quite easy to build up methodology, a framework around how do I execute this properly in my tool shop for me to know that I have consistency on my machine. The same goes with the physical process itself. There's a lot of learnings to be made both on the physical and the digital side. How does the machine use its in situ IR diode system to monitor the melt pool? What kind of wavelengths do I get from my emission spectrum from the melt pool? How do they transfer up through the melt pool camera system? Is it a coaxial system or is it an off-axis system? From that, you can derive a lot of how well the machine performs, where you should position your component within the build envelope for it to get the best sense of feedback if it's an off-axis system and so forth. And then the dirty little secret, post-processing. We will not talk much about that today because a lot of that is actually conventional manufacturing that's going on there. And if you are a bit rude, you could claim that powder bed metal additive is only a method for you to make a workpiece for subsequent CNC machining. I know it's stretching it a bit, but in many cases, we need to taper holes, machine surfaces, before we have a functional workpiece. So it's also not half a lie. So moving on, in order to be able to understand this, this big ecosystem, you need to be curious by nature. You need to be wanting to learn new skills within fields that are not your own. Some of the needed skills for you to be an expert in additive manufacturing, and this is generic, whether it's vat photopolymerization, whether it's laser powder bed fusion, you need to know about materials, you need to know about manufacturing engineering, you need to know about fluid dynamics, material science, optical systems, about computational geometry and precision engineering and electrical engineering before you really begin to be able to encompass all the aspects of additive manufacturing. And of course, here it's totally fine to build up expertise in some select disciplines among these ones that I've listed here, but don't be afraid to spread your knowledge if you plan to make a career within additive manufacturing. That is what we've done in our group. Our group is really built up by jacks of all trades, of specialists within different fields. I have a straight up computer scientist employed in my group, and a straight up chemist. And also, since the term additive manufacturing is an umbrella term for so many different manufacturing processes that it is almost as if you were saying conventional manufacturing, where vat photopolymerization and laser powder bed fusion are two very different processes, and they both differ just as much to compare it with, for example, cladding. Then what we have been doing in our group is to map out which processes are most relevant for us to work with. So here I will showcase two systems that we've chosen to work with in our group. The first one in metal additive being laser powder bed fusion. And this matrix shows you also all the other ways by which you can manufacture additively in metals. And then in terms of polymers, we've gone with vat photopolymerization. That's because of a fun little phenomena here in Denmark. We totally dominate the global hearing aid industry. Every other hearing aid produced on planet Earth has come out of the factory of a Danish company. We have more than 50% market share. And the vast majority, more than 95% of the custom fit hearing aids that conforms with the individual patient's ear tract comes out of vat photopolymerization machines, the machines that you would also know as SLA or DLP machines. And therefore, it has made a lot of sense for us to specialize in that system as well. And we've done that not by collecting the best industrial machine tools out there, because we do not want to be forced to be mere operators of a machine under some very restrictive regulations from the machine manufacturer. We want an open research platform. We want to be able to take this holistic, systemic approach to additive manufacturing that is hard to do on a commercial system. For the two systems I will be showcasing today and how we've achieved excellent print resolution on them, I would like to first start talking about photopolymer additive manufacturing, or SLA, or DLP, or whatever you choose to call it, this one. As you can see, the machine in this photo is not a standard machine. We built it ourselves. It's quite simple by nature. We have one linear stage. We have an optical system, a protection unit that can expose the workpiece to ultraviolet light. And we have a resin container containing our photopolymer that chemically reacts upon exposure to UV light, and having a glass window in the bottom of the vat. So let's consider this system. There's a stage in there. Stages are well known. CMM, for example, a 3-axis coordinate measurement machine, has 27 well-mapped errors coming off its stages. And these are flatness, pitch deviation, yaw deviation, straightness, backlash. We can all understand them. And we can relate errors we see on the workpiece to this stage. In our case, despite the fact that we had invested in a $15,000 to $20,000 expensive linear stage, we had this issue. There was a bump on all our parts. And what I then came to realize is that one of my poor Ph.D. students managed to collide the stage into the vat, and was afraid to tell anybody because they were afraid that they had harmed the machine. And what you know they had. There was an easy solution to that. Just make sure that we are using another area of the stage. So basically, we changed the length of this rod so that future builds were not where this little nook or bump on the stage had appeared, and then problem solved. There's also an optical system in a Vat photopolymerization machine. The errors in that is well known. It's fisheye, it's barrel effect. We can have keystone errors, we can have schooners. And it's very easy to understand. If you go and look at, for example, there's a wonderful open source code called the Camera Calibration Toolbox that is used within computer science for image analysis for calibrating cameras. And that toolbox can be modified to be used to fully map out all the optical errors you have in your Vat photopolymerization system. If it's an open system such as ours, we can use that toolbox to create compensation masks for the image field such that these effects are being compensated for in software. Could also try to fix it in hardware. It's a bit more cumbersome, then you need to work with your lens stack, but it can be done super easy to fix in hardware. No, sorry, fix in software. We also know that in many cases, the image is generated by a DMD device, this micro mirror device that contains millions of small mirrors, each representing a pixel that either beams the light up through the barrel of the Vat photopolymerization machine, or throws the light into a beam dump. Now, these pixels are square. And one way to know if you have managed to have found your focus on your machine is that since your image is generated by pixels, for example, if you approximate a cylinder, you would end up with something like that. And if then underneath an optical microscope, you see that surface being represented in the surface of the component you have manufactured, you know that your machine is in focus. You know that you have properly calibrated the distance between the vat and the image field of the projector. If you do not see these pixels, you are not in focus. You will blur all features and you will reduce the fidelity of the finest features you can make. Again, these things can only be learned by you really being intimate with the process, not being afraid to try to understand the underlying mechanisms by which it works, using holistic approaches. Then what you can do, if you look at these small holes, they are not pixelated. Then you can begin to use your knowledge to your advantage. This is a little filter made in photopolymers that you would never want to machine or emboss or engrave using a laser. Basically, you would not like to make this filter, primarily because of the aspect ratio of the holes. But we have such an easy time making this filter using our additive manufacturing system. And the holes are more well-defined than what you would expect to see on an industrial equivalent machine. That has been achieved because we have made our own software for the machine as well. The entire control interface to the software is our own software that we have been developing over the last 6 years. We have some advanced calibration settings we can work with this machine, such that we can deliberately defocus the video projector. The entire video projector inside the machine sits on an elevator mount, so that we can move it out of focus and then get rid of the pixelation effects that otherwise would be given by being in focus. But we can also do fun things in software. Now, one of my computer scientists has a background in appearance modeling. That is, how do I take a 3D file of a geometry and represent that as lifelike as possible through rendering. And if you're really good at what you're doing, you end up making animations for CGI in Hollywood movies. And then we've coined a new word, appearance manufacturing. What now if we apply the same algorithms that makes computer graphics looks nice, such as, for example, this is a line drawn just using a simple Bresenham algorithm on a computer screen over the diagonal of the field of view of the screen, whereas here we have used anti-aliasing to blur that transition. And you will see that being represented in the part you are printing as well. That here you have, each time you have built some layers, you need to step in 1 pixel on your DMD chip to continue making this diagonal or this conical geometry, and you get the staircase effect. Whereas here we have a smooth transition, we blur out the layers. We are actually so good at controlling this that now we can ask the machine to cure half a pixel for us, because we will have light from within the geometry being scattered and dissipate out into the black pixels of the image field. And then if one of these pixels are only slightly turned on, then we have just enough light in the interface between the fully lit pixel and the dimmed pixel for us only to cure half of it. And that means that we can push the print resolution of the machine to where we can embed holograms on the surface of the components we are printing, as you know, from a credit card. So this is a little 12 by 12 millimeter block where you can see that we have embedded our university logo on it. You will see that we also have some geometries here. This one has a matte appearance. This one has a nice specular reflection standing here. That's just us asking for the appearance in software. Here we are adding Gaussian noise to the image masks, and here we are not. Same goes for this bunny rabbit here. That's just for us to show that we can do this on any arbitrary surface. That this one has a generally matte appearance. This one has nice specular reflection standing on many parts of the surface of the bunny. Again, by adding in Gaussian noise here, by using anti-aliasing on this one. We in fact have been able to push our print resolution so much down that we are beginning to struggle with the question that is, what should we use this for? Here we have a little 1 by 1 by 1 millimeter bunny printed in photopolymers. This is an order of magnitude better than what you can do on an industrial system. You see no layering effect. Here it is again, even smaller. Now it's 0.5 millimeter by 0.5 millimeter by 0.5 millimeter. And the lines you can see throughout the geometry is actually scratches we had on the glass bottom of our vat in our machine. So we can push the machine this much because it's an open system. If the industry provided us with open systems, we could do the same on the commercial machines you have in your labs right now. So quickly moving on to metal additive, we are out of time and I think I will be done in some 5 minutes. We have taken the same approach. This is our additive metal powder bed fusion system. It's not a Renshaw or an Islam Solutions or a concept laser system. It's our own. It's an SPI laser. It's Thorlabs optics. We are currently upgrading the optical system to Jenoptik, that is of a much higher quality, and to a 1 kilowatt laser. This is our recoder. This is our build chamber. This is the process run. I hope the video plays okay over the interwebs. And we are able to not only produce nice parts with a density up to 98, 99%, we can also make functionally graded parts. So in this case, the bottom part of this material is 316L, the top is MS1. And we are able to either make an abrupt transition from one layer to the other, or do a functionally grading where we blend the powder throughout multiple layers as we build our component. Here's a bit of showcasing of how that affects the hardness that increases. And we can see the microstructure of the component as well. And by mapping out the chromium content that is much more present in the one than the other, we are able to do an elemental map of the surface, as you see here, where you can see how well we are able to control mixing these two very dissimilar materials. Again, we are able to do things that you would never ever be able to do with a commercial system. Our journey into open metal powder bed fusion systems is somewhat new. We've only been at it for some 3 years, 2.5, 3 years by now. So we have the machine up running. There's still so much to be learned from our open system. We are slowly approaching where we have the same print quality as industrial state of the art. But if you look at what we've done on photopolymers, we are way beyond state of the art already. And I would never ever buy a commercial system for our lab. I would just replicate one of the open machines that we have already. So the learnings from this presentation is that we are currently being offered a black box by the industry, and we need to somehow figure out how to work around that. I really endorse taking a holistic approach to make sure that you understand what goes on inside your machine, and don't just stick your head up where the sun don't shine and then do CT scanning of your component like everybody else, all the other researchers on planet Earth. Be a systems thinker and try to decompose the machine in front of you into subsystem, and those subsystems into their subsystems, because then you really begin to be able to advance what you're doing, push the industry to provide us with open architectures, or even better, push yourself beyond industrial excellence. It is not that difficult. We were able to do it in our lab. So can you. And in fact, I can tell you that we will be releasing our Vat Photopolymerization platform on GitHub, providing you with a full bill of materials of all the components going into it, what video projector we are using, how the computer should be spec'd to run the software itself, all technical drawings, build styles for 20 widely available photopolymers. And then you will be able to, more or less like an IKEA furniture, to assemble it yourself. There are some components to which we provide technical drawings that you need to send off to your local tool shop to get them manufactured. But else it's very easy to build it. And in a few years, when we are beyond state of the art, industrial state of the art on our powder bed metal system, we will release that to the general public as well, following an open source mindset. So with that, I've had the pleasure of talking straight up for some 35 minutes, and we've reached the end of my presentation. thank you so much for spending an hour with me and listening to my view upon how to push additive beyond state of the art.